Morning, good afternoon, everyone. My name is Raman Bhati, and today I'll be presenting my mini Pascal compiler project for CS465. This project implements a complete compiler that takes Pascal source code and transform it through multiple phases from lexical analysis all the way to x86 assembly code generation. By the end of this presentation, you will understand how each phase works, the design decisions I made, and see a live demonstration of the compiler in action. Let me start with an overview of the compilation phase I implemented. A compiler is essentially a pipeline that transforms source code step by step into an executable machine code. My mini Pascal compiler implements five major phases: lexical analysis for converting characters into token, syntax analysis for parsing tokens into a structured tree, semantic analysis for checking types and meanings, intermediate code generation. Before that, I also do symbol table management. That's also like part of the first two, tracking variables and their properties. The next one is intermediate code generation for producing the three address codes, and finally, the assembly code generation for producing x86 machine code. Each phase builds upon the previous one, and together they transform human readable Pascal code into executable programs. We'll start with lexical analysis, which is handled by my lexer class. The lexer's job is to read the raw source code character by character and group them into meaningful units called tokens. For example, when the lexer sees the character I and F together, it recognizes them as if keyword token. When it sees 123, it creates a number token with the value 123. The key features of my lexer include position tracking, meaning every token stores its line and column number, which is crucial for error messages; comment handling, which supports both curly braces and parentheses, Pascal comment styles; case insensitivity. The Pascal keywords are case insensitive, so begin capital all caps and begin all small letters are all equivalent. And then literal support, which handles strings like hello and characters like capital A as is. The lexer continues until it reaches the end of the file, producing a complete list of tokens for the parser. Now that we have a stream of tokens from the lexer, let's move to the next phase where these tokens are organized into a meaningful structure. The next one is syntax analysis, or it is also called parsing, which takes a flat list of tokens and organize them into a hierarchical structure called an abstract syntax tree, or AST. I implemented a recursive descent parser, which I chose for several important reasons. Simplicity: each grammar rule becomes one function in my code. Readability: the code directly mirrors the grammar structure. Debuggability: I can step through with the debugger to understand exactly what's happening. And finally, flexibility, which is easy to add semantic actions during parsing. The parser works by examining the current token to decide which grammar rule applies. For example, if it sees an if token, it knows to parse an if statement. If it sees an identifier followed by colon uh, equal to operators, it knows to parse an assignment. The abstract syntax tree that gets built abstracts away syntax details like semicolons and keywords, keeping only the essential program structure. For instance, the expression in brackets x plus y multiplied by 2 becomes a tree where the multiplication is the root with a subtree for the addition. With the abstract syntax tree built, we now have a structured representation of the program. Let's look at the specific methodologies I used in each phase. Let me explain the methodologies For lexical analysis, I used a character by character scanning approach with look ahead. The lexer maintains the current position, line number, and column number. It uses a peek function to look at the next character without consuming it, which is essential for handling multi character tokens like assignment operators or greater than or less than equal to operators. For parsing, as I mentioned, I used recursive descent. The key insight here is that each parsing function handles one grammar rule. Lower precedence operators call higher precedence function first. For example, parseId would call parseMul before processing addition, ensuring multiplication happens first, exactly matching the mathematical convention. The parser builds abstract syntax tree nodes as it recognizes the grammar constructs, creating a tree structure that represents the program's logical organization. For semantic analysis, I integrated the type checking directly into the parsing phase. As each AST node is created, I recursively infer its type using the infer type method. The method examines the node type. If it's a number, return integer. If it's an identifier, look it up in the symbol table. If it is a binary operation, check both operands and determine the result type. For intermediate code generation, I emit three address code instructions as the AST is traversed. Each complex expression is broken down into simple three operand instructions using a temporary variables like t1, t2, t3 and so on. The TAC emitter class manages these temporaries and generate unique label for control flow. For assembly generation, I traverse the AST again, this time producing an x86 instruction. Variables are stored on the stack relative to the base pointer, and I use the C calling convention for printf and scanf to handle IO. My mini Pascal compiler supports a substantial subset of the Pascal language. The data types like integers for whole numbers, characters for single characters, boolean for true false value, operators like arithmetic, plus, minus, multiplication, division, mod, booleans like and or not, comparison operators like equal to, less than or equal to, greater than or equal to, not equal to, all that. Similarly, control flow statements like if then else, while do loops, and begin end blocks for grouping statements. IO operations are also there, supported. Read for input, write and write ln for output. Support for printing messages, integers, characters also there. Let me explain the key data structures starting with the token class. Each token class has three essential fields: a type, a string that indicates a token category like ID, number, or assign, the value, which is the actual text from the source like my variable or 42, line and column, the positions in the source file. The position tracking is crucial when I report an error like type mismatch at line 15, column 8. This information comes handy from the token. Without it, user would have no idea where to look in the code. Example tokens include, program, var, begin, end, if, then, else, while, all that. Operators like plus, minus, assign, all that. Identifiers like ID for user-defined names. The symbol table tracks all declared variables using the symbol info class. Each symbol entry contains the name, which is the name of the variable, type, which is of the data type, could be integer, char, boolean, anything. Scope level, the nesting depth where 0 means global scope. Address, the memory offset from the base pointer. And finally, the size, how many bytes the variable occupies. For example, when I parse var xyz integer, the symbol table creates three entries: x, which has the address 0, size 4, y, which is the address 4, size 4, and z, address 8, and size 4. These addresses are assigned sequentially, and this directly determines the stack layout in the generated assembly code. The structures work together. Tokens feed into the parser, which builds the AST while populating the symbol table. The AST is then used for type checking and code generation, with the symbol table providing variable information throughout. For managing multiple scopes, I use scope table class combined with the stack-based small symbol table manager. The scope table uses linked hash map to store the symbol. Now here I specifically chose linked hash map over the regular hash map for an important reason, because they maintain the insertion order. This means that the variables are stored in an order they are declared, the memory addresses are assigned sequentially, the output is deterministic and predictable, and debugging becomes much easier. The symbol table manager maintains a stack of scope tables where when the parser enters a begin end block, it pushes a new scope. When it exits, it pops. Looking up a variable searches from the innermost scope outward, implementing proper lexical scoping where inner variables can shadow outer ones. Now let's talk about some design choices or design decisions I made. Recursive descent over parser generators. The parser generators like YSCC or Antler could have been faster to develop, but recursive descent gave me a complete control and understanding of parsing process. Since Pascal has an LL1 grammar with no left recursion, recursive descent works perfectly. As I mentioned, maintaining insertion order is crucial for the predictable and debuggable output. I decided to use linked hash map since the hash map would give me random order. Tree map would give me an alphabetical order, neither matches the declaration order. I chose x86 as the target because the generated code can actually run on real hardware. Um, People in this class can compile and execute the output immediately, making the whole compilation process tangible. Alternates like LLVM-IR would require additional tools, and JVM bytecode would require a Java runtime, of course. Uh, I integrated the semantic analysis so this decision was made because in a single pass this is efficient and straightforward for a simple language like Mini Pascal. A separate pass would be needed for more complex type with forward references. Semantic analysis. Um, this ensures that the program is not just syntactically correct but also meaningful. My implementation checks for undeclared variables using a variable that was never declared, redeclaration, meaning that declaring the same variable twice in the same scope, type mismatch, which is assigning a boolean to an integer variable, invalid operand, meaning using strings with arithmetic operators, and finally condition types, which is ensuring if and while conditions are boolean. The type inference works recursively. The numbers are integers, characters literals are char, boolean literals are boolean. For identifiers, look up the symbol table. For binary operation, check both operands and compute the result type. Errors are collected with their source position and helpful error message. Error management is essential for usable compiler. My error handling strategy includes error recovery. When an error is found, the parser doesn't stop immediately. It synchronizes to a known good point, typically a semicolon or end keyword, and continues parsing to find the additional errors. Error bubbling. Errors at one phase propagate appropriately to the later phase. If a variable is undeclared, it gets an unknown type, which prevents cascading type errors. Phase level correction. Each phase handles its own error types. The lexer handles invalid characters, the parser handles syntax errors, and the semantic analyzer handles type errors. Finally, we have descriptive messages. Every error includes the line number, the column number, and a clear description of what went wrong and where. The three address code is my intermediate representation between the abstract syntax tree and assembly. Each three address code instruction has at most three address, a result, and up to two operands. The format is simple: T1 equal to A plus B for binary operations, T2 equal to minus T1 for unary operations. If T1 go to L1 for conditional jumps and go to L2 for unconditional jumps. I chose TSC over static single assignment because TSC is simpler to generate and understand, while SSS optimization's benefits are an overkill for this small project. The TSC emitter class generates TSC instructions. Here is how an expression transform. If you have an expressions like x equal to 3 plus 2 multiplied by 5, we could convert this into a TSC by just assigning T1 equal to 2 multiplied by 5, T2 equal to 3 plus T1, and x equal to T2. For more complex expressions, it would become a lot more temporary variables, which is also one of the problems with three address codes, that it will have a lot of temporary variables if the expressions are long. The final phase generates x86 assembly code that can be assembled and executed on any modern Intel or AMD processor. The generated code includes a data section for string constants and format strings, a text section for containing the actual code, proper stack frame setup with push queue and move queue calls, and then the variable access through the base pointer offsets. Finally, the assembly level code generates generator handles different output types. So the first example shows that the string output, it calls the text section and string address into the first argument register, which is RDI, and zeros the return register and calls the printf. So this is the presentation part. I will start the demo now. Okay, so this is the beginning of the demo. This is our main module, which is responsible for calling all the other modules. On the left hand side, you see the project structure. Since this is a Java project, so everything is under the UND compiler module. All the packages are defined in here, and the code is organized accordingly. So for example, in this AST module, the main node is the abstract syntax tree node, which is an abstract class here, which has a pretty print method, as well as the line and column variables or member functions. All the other classes you see in here, like if, id, or assign, or unary, while, anything you can think of in a Pascal function, code, everything here is added as a node, which we support. So everything that is added as a node, so that it will help us in later on, creating the AST abstract syntax tree. Now, moving directly to the IO main.java, because this is the main function, and that's where the whole thing is getting orchestrated. Basically, it makes a call to, or it reads the file which is passed from the command line, and that should be a Pascal file. So I'm testing this with two Pascal files. One is the standard sample.pas Pascal, and then the other one is sum of two numbers.pascal. This is a very simple Pascal code which I have run before, and this is the standard sample provided by Dr. Reza. in the Blackboard. Now, parser is the meat of the whole um, program. But without any further ado, um, let me just run the code and show how it works. So I was able to debug it and run it, and as you can see, right now it is showing all the three address codes. So each temporary code is created, right? So T8, T7, T6, it's incrementally created um, for, and it is being used. It is being created using the AST. So AST is helping in that. But before TSC, let's go to the symbol table and see how the symbol table was generated. Right. So this is the symbol table. So we have already seen um, the Lexer output, which is the tokens. So that's why I've disabled the token part, so that we don't clutter this space. So from symbol table, you can see that there are four variables and their types, their level meanings, at what nested blocks they are in. So 0 means at the global level, and 1 means nested block 1, 2 means nested block inside the first block, and so on. So everything is on the top in the global level, and then everything is a size 4, right? So three integers, 0, 4, 8. They are sequential because it helps to create the assembly code. I haven't been able to complete the assembly code part, so I'm just running till the three address code. Hopefully, before the deadline, I would be able to finish the assembly code part as well. But this demo is still three address code, and then sizes for each. All right, so each scope, I mean each variable and their sizes. Now this is the symbol table. Let me quickly go and show how the symbol table manager was able to run that. Right, so we have um, this code, and actually there is a symbol info table as well somewhere. Yeah, here. So symbol table info allows you to have name, type, scope, level, address, and all those information. So this allows basically to capture the variables, and we can validate against the symbol table if something is redeclared or undeclared, and so on. So this is where the symbol table comes into the play. um, the scope table which I was showing earlier, right? So 0000. So this is basically is what responsible for that. Anything which is defined at the global level, that is assigned as 0, and then it calculates whether the next declared variable is in the same scope or it is in the nested scope. uh, yeah, so that's about it. And then moving on to the AST part itself. So as I said, I showed AST before, right? So um, let's take an example of block node, or let's say ID node, or if node. Basically, if node is easier. It has basically more items, right? So condition, meaning the if node, if is also an AST node, then statement which is also an AST node, and else statement. So you initialize the AST node if node, and let's see where we are using this, right? So in this case, it goes for the TSC, but even before the TSC, we use it for creating the AST itself, and um, basically it generates, it calls the recursive descent algorithm. I mean, it recursively calls the functions and generates the the tree itself. So we have identifier X and identifier Y, defined at the top, and then this is the first um, expression, right? So we have got 2 multiplied by 5, so that's executed first, and whatever the result of this is, it is added in number 3. So and then it is finally assigned to X. So that's the tree representation of the expression which is provided in the input. So the whole tree is built like that, using the recursive descent parsing, which I can show you in the parser part. Yeah. So anything you see here, right? So parse. So as soon as it goes to parse block body, or even before that, let's say it goes to this parse program function, right? So this is the first part of the whole file. Um, so we know that the scope is going to be global at that level, and it checks whether it has the program. If not, then it calls the error function. If it has the program, then it checks for the IDs, and then there is another you know um, for example, it has that program example, and then left parent and right parent, um, and this id comma, it will continue until it reaches the right parent, right, and so on, until it goes to semicolon. Similarly, so yeah, this is where the parse block body is called. Now inside this parse block body, you see we are calling this parse statement, which is a recursive, which is following the recursive descent algorithm. So parse statement is calls itself multiple times within the function. So it mimics that grammar basically, and each function here you can see is actually um, mimicking that recursive descent parsing. So here as well, we are calling the parse statement is within the while loop, right? Um, Parse expression is called. So this is basically again another example of recursive descent parsing, where it says a uh, tends to a b, and then the b is this guy, so it can go to b, or it can go to a. So that's another example of that. But yeah, this is basically it. I and yeah, this is another example of calling the parse statement within the parse statement function. So yeah, I think I have covered most of it. I was not able to implement the machine level, assembly level code generation so far, but I have few days left, so I'm planning to implement them by then. But that's about it. Thank you so much.